Okay, great. So our next talk of the session will be a merge talk. The first speaker will be Mischa Woods.
Hello? No.
Oh, sorry. The first speaker will be Sepehr, contrary to the schedule, and the second speaker will be Mischa, and they'll both be telling us about symmetries and approximate quantum error correction.
Yes, thank you. And I don't have a pointer somehow. It works. Is working? Oh, I see. Okay, thank you. Yes, thank you for giving me the opportunity to speak here. I'm Sepehr Nezami. I'm going to talk about this for continuous symmetries and approximate quantum error correction, which is a joint work with Philip Feist, Victor Albert, Grant Salton, Fernando Postowski, Patrick Hayden, and John Preskel. And then I'm going to hand it over to Mischa, who's going to talk about the joint work with Alvaro on continuous groups of transversal gates for quantum error correcting codes from finite Kullak reference frames. So I'm going to start. I'm going to give you a joint motivation for both work, and I'm going to present our results, and I'm going to hand it over to Mischa to talk about their results and conclusions and outlook. So yes. So I'm going to talk, the main concept here is symmetry and quantum error correction. I'm going to talk about how these two notions have a conflict, and my goal is to formalize and understand this conflict in next slides. I have to tell you what is a quantum error correction setup that we are talking about. Is you have a isometric encoding that mapping a logical Hilbert space to a physical Hilbert space that contains n subsystems. And in this talk, I'm going to talk about focus on erasure corrections of a single physical subsystem, which is basically the worst thing that can happen on a single subsystem. But in the paper, we talk about more general things, and also Mischa will talk about those things. And then the important notion is that what I mean by a system that has quantum error correction and symmetry, and that's the notion of covariant codes. So basically, suppose that you have a symmetry group G and representations of this group G acting on different subsystems. And we say an encoding is covariant if you act by the group, and then encode is going to be same as encoding and acting by the group representation on the physical subsystem. In other words, covariance means that if you rotate on an encode, it's same as encoding and rotating. And it's importantly here we have a tensor product representation operator acting on the physical Hilbert space. We can relax that condition a little bit, but I'm going to focus on this construction for this talk. And why we care about this kind of covariant codes? Because they happen in multiple scenarios. For example, you have reference frame quantum error correction when you have two parties, Alice and Bob, that are unaware of each other's relative orientation in the space. And still, Alice wants to send a directional information to Bob through a noisy environment. And she wants to do some quantum error correction. And in this setup, you can see that the problem reduces the covariant quantum error correction, as I explained before, and the task cannot be done perfectly. Another example is in condensed matter systems, when you would like to encode your logical information in the subset of the physical Hilbert space, in the subset of the Hilbert space. And again, you might have Hamiltonian time evolution acting on the logical Hilbert space and the physical Hilbert space. And in these cases, the time translation symmetry is a symmetry that's covariant, that the code is covariant for this. And another prime example is holographic duality, when you have this gravitational system in the bulk, which is dual to a conformal field theory non-gravitational system in the boundary of this space-time. And by this duality, we mean that there is a mapping that maps whatever happens in the bulk, in this gravitational side, to the boundary. And it was importantly observed that this mapping itself is an erasure correcting code. And again, this type of codes are covariant with respect to the time translation symmetry. And our last example is fault-tolerant quantum computation. I'm going to expand on the next slide because it's more important for us at this stage. And I'm going to explain that using the Eastin-Knill theorem. So suppose that you want to do fault-tolerant quantum computation. And ideally, you want to have a code that can do the two things: to correct erasure of a single subsystem. It's a good quantum error correcting code. And also, you want to be able to transversally implement a universal set of logical gates. You want to be able to implement any logical unitary by a tensor product operator in the physical Hilbert space. And that would be favorable because then the errors in the implementation of any one of these physical operators will not propagate to other subsystems. So that would be nice to have this. But it was shown that there is no code with these two properties. And in fact, they showed that there is no perfect quantum error correcting code which is covariant with respect to a continuous symmetry. And the point of view you're going to take here is that we do not necessarily want to have a perfect code, but we might be able to tolerate some errors. So I'm going to study approximate quantum error correction of covariant codes, symmetric codes, and I'm going to prove an approximate version of the Eastin-Knill theorem. So let me start. So first, when do covariant codes exist? We're going to study this question in multiple scenarios when you have a finite symmetry, or you have a continuous symmetry, or you have a finite dimensional encoded space and have infinite dimensional encoded space. And you can see that if you have finite symmetry and finite Hilbert space, or continuous symmetry and infinite Hilbert space, you can basically construct codes which are covariant, which means that there is no conflict between quantum error correction and symmetry in these regimes. But Eastin-Knill theorem tells us that when you have continuous symmetry and finite dimensional encoded space, then there is a conflict. You cannot have perfect codes. And for this talk, we're going to focus on this regime in this scenario, the regime. And then what we're going to do is study approximate quantum error correction. We're going to prove strong upper bounds and quality of these codes. We're going to ask if you have a covariance, if you have symmetry, what's the best you can do? Prove an approximate version of Eastin-Knill theorem. We construct high-quality symmetric quantum codes. And then I'm going to hand it over to Mischa, who's going to talk about connection between Eastin-Knill theorem and Pauli's perfect clock no-go theorem. And he's going to tell you how to transform quantum error correcting codes into high-quality approximate transversal gates using clocks and reference frames. So before going into the details, I'm going to tell you intuitively why this Eastin-Knill theorem holds and why there is no symmetry, why there is no perfect quantum error correcting code with a continuous group. And the reason is that continuous group has generators that are called charges. And when you have a covariant code, you can observe that the charge is conserved, meaning that if you compute the expected value of the charge operator in the logical Hilbert space, it's going to be equal to expected value of this charge operators in the physical Hilbert space. And that is a problem because quantum error correction works if the individual physical subsystems are totally independent from the logical Hilbert space. They should be decoupled. But now you know that because of charge conservation, at least the information about the charge value will leak to the environment and leak to the array subsystems. And that would prevent you from having a perfect quantum code. And we're going to build on this intuition and study approximate quantum error corrections. And our figure of merit here for measuring how good codes can operate is worst-case fidelity of entanglement fidelity of recovery. And basically it works like this. You have the encoding, and you have the erasure happening, and then you choose the best possible recovery. And at the same time, you're going to choose the worst-case state, which has the lowest possible fidelity. And this fidelity is called the worst-case fidelity of recovery. And my measure is this epsilon, which is basically a square root of 1 minus this fidelity squared. If you did not follow this, if epsilon is 0, you have perfect code. And for large epsilons, you have bad codes. And now I'm going to tell you the first bound that we have is telling you that the epsilon is lower bounded by 1 over n, which is the number of subsystems, times delta t L divided by delta ti. And this delta means that difference between the maximum eigenvalue and the minimum eigenvalues. It's basically size of the operator. It's the infinite norm. So it's kind of intuitively makes sense. If you have more subsystems, you have going to be less information about the charge value leaking to each one of individual subsystems. And if you have larger delta t, you have more room to hide your data. And the very fact that this lower bound is non-zero means that you can't have perfect code. So it's an extension of Eastin-Knill theorem. But things are going to get much, much better if you go to the non-abelian groups. And there you can construct bounds which are depending on the dimension of subsystems and not the generators. You can prove approximate Eastin-Knill theorem. I'm going to tell you quickly why by an example of U2 group. So suppose that you have this U2 group and the logical dimension is 2. Then you would know that the charge operators or for example, spin j operators have eigenvalues going from minus j over 2 to plus j over 2. And delta t, the size of the operator, is j, while the dimension is 2j plus 1. It's basically telling you that dimension over 2 is lower bounded by the size of the generator, and it's a relation between size of the generator and the dimension of a space. And you can just substitute this relation into our bound, and you get a bound for epsilon for the error, which is lower bounded by now 1 over n, and also 1 over maximum physical dimension. So this is a bound for SU2, but things are exponential in our favor if you look at the representation theory of UD and you go to higher logical dimension. And you can have this very complicated bound. But before explaining that, I'm going to give you this, remind you what the setup is. You have this encoding, and you want to be able to implement this unitary group, a logical unitary group, by a tensor product operator and the physical subsystem. And by doing representation theory, I'm just explain, looking at the eigenvalues of these generators, you can find this bound, but it's hard to interpret, so I'm going to look at these different regimes. So suppose that you want to keep the epsilon constant and dl large. Then you can see that in this regime, the epsilon, the error, going to be lower bounded by 1 over n times the ratio of the number of logical qubits to the number of physical qubits. So now instead of dimension, log dimension appear in the bound. And for example, if you want to encode 20 qubits into 3 subsystems, you want to keep your error around 1 over 1,000, you need 2,000 physical qubits. And the other regime is that suppose that you want to have a good enough code that can distinguish different basis elements, logical basis elements, and you can see that in this case, our bound tells you that you require exponentially many physical qubits. So with this bounds, I'm going to hand it over to Mischa. Oh, I have to. Sorry.
Okay. So everyone can hear me? Yeah, okay, good. Yes, okay, so as Sepehr said, what I'm going to present now is joint work with Alvaro Alhambra, who is also around. So if you also have any questions you'd like to ask him, he's should be around to answer your questions as well, like in tea breaks. Okay, so the motivations for this work have been already provided by Sepehr. So I will now go into our particular construct. So what we were interested in is generating lower bounds, lower bounds with explicit constructions for which hold for any error-correcting code. And in particular, we focus on the U1 case because it's relation with clocks, and also because it's if you go beyond the abelian case, you suffer strong constraints, as pointed out by Sepehr. So in some sense, it's more interesting. So so what we want to do is take so we want to have a construction where, given any encoding, any error map, and any decoding map, we'll take this error-correcting code. We will add some clocks, so m d-dimensional clocks to the code space in such a way, with such a formalism, such that we get out a new code which is covariant with respect to SU1 symmetry, a new error map which is the old error map on the original code space plus new error map on the clocks, which is like an extension of the code space, and a new recovery map. Okay, and the difference to this new error-correcting code in comparison with the old one is that the old one was perfect in a sense because, in principle, so we assume here you can recover perfectly, whereas here as Sepehr pointed out, it won't be possible to recover perfectly. So we'll have some errors, and we'll go about bounding those errors. Okay, so we took our inspiration actually from a paper from 2017 from Patrick Hayden, Sepehr, and co-authors, where they pointed out that, that you can use reference frame alignment to construct covariant error correcting codes. So if you specialize to the U1 case, their formalism can be written in this form. So basically what they did is they took the original code and then made a rotated version and tensor product in some a U1 reference frame, and then integrated over the Haar measure of this setup. In their case, they had a perfect error correcting code. So, of course, in principle, you may ask, oh, how is this possible? Because wouldn't it violate Eastin-Knill, given what we've just heard? And the answer is no, because they assumed a perfect reference frame in this setup. And they showed that this necessarily lives in infinite dimensions. And one of the caveats of the Eastin-Knill theorem is that it assumes a finite dimensional code space. So this is a way of circumventing this Eastin-Knill theorem. What we then noted, though, is that this U1 reference frame is nothing more than as a clock, in the sense that it's some quant system you can think of it as evolving, and then you have some operator, some self-adjoint operator, which you associate with time. So when you measure it, you can get back with time. But if it's perfect, you'll do this perfectly. And then so in quantum mechanics, as I'm sure a lot of you are aware, people say that there's no time operator, right, in quantum mechanics, which is different to other observables, for example, position, where we have position operators. And if you trace back the origin of these statements, you find they go way back to the founders of quantum mechanics, when Wolfgang Pauli basically asked the question, do we have perfect clocks in quantum mechanics? Or in other words, does there exist a self-adjoint operator T and a Hamiltonian, such that in the Heisenberg picture, the derivative of this operator is the identity for all time. And he concluded that no, because the only solution up to unitary equivalence is when the time operator is the position of a free particle in one dimension, and the Hamiltonian is the momentum operator or generator of translations. Okay? There are some subtle points here that I won't go into that later people talked about this, but the main point is that here this Hamiltonian is unbounded from below. So Pauli concluded that all physical Hamiltonians are bounded from below, and therefore this cannot exist because one would require infinite energy. So basically this perfect U1 reference frame, we can think of it as it lives in infinite dimensions, which in principle is fine, like we all have harmonic oscillators and perfectly well-defined quantum systems. But the downside is that it also requires infinite energy in the sense of having no ground state. So this kind of this observation motivated us to then study imperfect, imperfect clocks of finite dimension and dimensionality. And the nice thing is that people have studied these clocks quite a lot, so there's quite a lot of examples in the literature, and we could use these to see how well one can create a covariant error correcting code. So we studied basically three regimes. The first two regimes, one can characterize of this form where the clocks are just m copies, okay, tensor producted together, and then here in the first regime we looked at the case of what we call T incoherent clocks, meaning that there exists some time such that in the periodic orbit of the clock it must commute with the time operator you use in the decoding. Okay. And it turns out that for this clock, this is it turns out that this is a big constraint on how well you can use this for decoding, because for these clocks we have an upper bound for some, so C naught is the dimension of the clock, independent of the dimension of the clocks. And you see it's upper bounded by this here, which is worse than the upper bounds that Sepehr discussed. And in particular, there's this well-known clock in the literature called the Saleika-Wigner-Perez clock, developed by these three authors in two separate papers. And these clocks saturate this bound. Okay, so they achieve this, but can't do better. But then in the second regime, we looked at clocks which do not satisfy, which are not T-incoherent. So for all times in their evolution, they never commute with the time operator. And in particular, we looked at these called quasi-ideal clocks, which were introduced by myself and Kohlfuss in 2018. And it turns out that these clocks, we can achieve a lower bound for the error. Oh, and by the way, so this epsilon is the same epsilon that Sepehr spoke about and introduced in his talk. So it's just a bound on the worst case entanglement fidelity. Okay, and here we see that now we basically get a square root improvement over these bounds. Okay, okay. And then what we did, we said, okay, well now, so that bound doesn't quite still saturate the bound of Sepehr. But then what we did is we said, well, what happens if we replace these M clocks with M copies of L entangled clocks? Okay, and basically, then what one can show is that the bounds from the previous slide still hold, but replacing the dimension of the clock by L times the dimension of the clock. And in particular, in the case of the what we call now entangled quasi-ideal clock, it still satisfies this relationship, okay? But now we get this bound here, which saturates the lower bound given by Sepehr and Kohlfuss. So now you see, and the thing about this bound is it's constructive and it holds for all error correcting code. So there's a protocol where you can take your error correcting code, you add your clocks, and you can achieve the optimal rate. We then also looked at so I didn't say as well, but here we're assuming erasure on the clocks as the error model, so for the clocks. So here we also looked at error models that go beyond this. I show a simple version here, for example, when you have just 3 copies of L entangled clocks. And then one applies an unknown phase to one of these blocks of clocks. Okay, so it's an unknown phase over the whole block. And it can be, it's completely random. So here, of course, if you naively just use the erasure on one of the sides, then with a probability of 1/3 of the time, it would be completely useless, right? So because you would use you would take the information from the clock that is where the time has been completely changed. So when you do the decoding. However, we found that there's a more intelligent strategy where if you make local measurements, you can basically, up to high fidelity, you can deduce where the error must have occurred, and then we can get a bound, a lower bound on what's achievable of this form here, which is not as good as if we had erasure at known locations, but still it goes to 0 for large dimensions. The other thing briefly want to discuss as well is randomized constructions. This is from Sepehr's paper, where they show that they have existence proofs of bounds for general UD, where you have to randomize over the isometries and the irreducible representations. Okay, and here you can also achieve these bounds here, which are quite good. And these are, as I said, existence proofs. So one minute. Okay, yeah. So now I'd just like to conclude. And as I said, basically a joint conclusion for both papers. So the first thing, the take-home message is that we have approximate versions of Eastin-Knill, and we've discussed applications. we have bounds on the fidelity for approximate error-correcting codes. And then some other message is that we have tight upper and lower bounds for error-correcting codes for the abelian case, if you combine both results from both papers. And then in the non-abelian case, Sepehr and Kolfers also have bounds that, but in the non-abelian case, you have the restrictions are much stronger than in the abelian case. So I said before we have constructions for the whole unitary group. Another important thing as well is that the bounds hold in the case of overlapping generators. So basically just local Hamiltonians. So this was not discussed in the talk, but this also holds in both papers. And then some open questions are the possibility of the randomized unitary covariant constructions, and can they be useful for fault tolerancy, strengthening the UN bounds, potentially use simple clock constructions for arbitrary Lie group covariant error-correcting codes, and how to, and more general error models, for example, photon loss, which I think is particularly interesting for experimentalists. Okay, so that's the talk, and you can ask either of us any questions.
Thank you, Sepehr and Mischa. We have time for a couple questions. Yeah.
So I guess a comment and a question. So I think the open problem question 1 is already answered in the results that Tamara Kohler will talk about this afternoon, that gives a construction of approximate error correcting codes that have approximate covariance under SU and under the unitary group. And what I wanted to ask is that these constructions are based on perturbation gadgets. And I was wondering if you knew, so these give constructions of approximate quantum error correcting codes that are covariant, and the number of physical qubits is polynomial in the number of logical qubits. And the reason it doesn't violate the bounds is that then I guess the gap in the operator norm has to grow super polynomially, if I remember right. And I was wondering if you know do these constructions that we have in our paper from earlier this year, do you know if they saturate your bounds, or is there still a gap between them? For either of you, I guess Sepehr is more relevant.
Well, so the answer is no. So this is something actually we briefly discussed with Tamara when she was visiting ETH. And it was something we thought would be interesting to look into, but it wasn't so obvious a priori to us. I don't know if Sepehr has any more insights to that.
Another question? Don't be shy. Everyone's ready for coffee and snacks? Okay, well, if there are no more questions, let's thank all the speakers of the session again.